Inferential statistics, reminder, is where we want to make some predictions about a population, or we just want to know things about a population, right? So we get this cloud I keep drawing here. That's this population that's hard to grasp. And then from that population, we do some random sampling, and we end up with a sample. When we get repeated samples, we build what's called sampling distribution. So repeated samples. Something's ticking on my desk, driving me nuts. Stop it. Let's see, repeated sampling leads to what we call a sampling distribution. And these are three different but related things. And welcome, Alejandra. Glad you could join us today too. All right. So I just want to look at a situation where we actually do know a population, look at some samples and see how the population, the sample, and the sampling distribution differ so that we can better do these inferential statistics problems like hypothesis tests and confidence intervals. And I'm going to stick mostly with proportions and means with a single parameter. The book does a lot with multiple parameters, and I'm going to worry about that in a week or two. So although we've done some of that, we're going to come back to it later. So the homework I've assigned just reflects the single for now. All right, so let's head over to StatKey. And your browser probably remembers it because you've been there so much this quarter. And the link in the video and in the chat here if you want to join me. And what I want to do first is I want to look at sampling distributions, and then we're going to go back to the theoretical normal we started to look at last class. So let's take a look at sampling distribution for a mean. And we looked at the baseball players one before. There's a sample of 877, which is the entire population of 2019 baseball players, Major League. And we have all their salaries here, so that would be a population. And then I can choose a specific sample size, like maybe size 30. And I can generate a sample from that population. So I'm just going to generate one sample for now. So I get this new sample, and notice its distribution here is a little bit different than that one. It looks a lot different because there's so few of them. If we put this into, if we grab the data and stuck it into one of our earlier StatKey things, we'd get a better view of it. But bottom line is, population here, this is usually this cloudy unknown thing we don't know about. I pull a sample out of it trying to figure out something about the population. So for example, this sample says, hey, the mean of this sample is about 5.375 million. So we think the population probably has a mean of around 5.375 million. Now the actual one is 4.51. When we make a prediction based on the sample, we never just give a single number, we calculate a margin of error. So we'll do one of those a little later. But this is one possible sample, and I could generate another one. And this time, this sample of 30 has a mean of 4.486 million. So population versus a sample. Next thing is a sampling distribution. That's where we have thousands of samples, all of the same size 30. So right now I have 1,002 samples here. Each point is the average of 30 randomly selected baseball players from 2019's population. And everyone is a little different. So if I point to a dot here, on the right it says, bottom right, it says the mean is 1.576 million. If I point to one over here, it says the mean is 3.211 million. What the central limit theorem says is that the mean of the sampling distribution should be very close to the mean of the population if you have a big enough sample size. Is 30 big enough? Sometimes. Okay. Bigger the sample, the better, but sometimes it's hard to take bigger samples due to lots of constraints, including financial. Let's generate thousands of other samples. So now I have three different things on the screen here. I have the original population, which is this crazy skewed distribution. Most baseball players make less than $1 million or around $1 million. There's a few that make an outrageous amount of money. Every sample here is different. So here's a sample down at the bottom, and I'm pretty much guaranteed based on the skewness of the population that each sample I pick is going to be skewed right also. So if we were to zoom in on any of these histograms down here, we'd see a skew right on them. Everyone? Not quite, but most of them, just due to the nature of the population. And let's see, 5,000, 6,000, and the computer's struggling to calculate this. That's a lot of work. right? It has to pick 30 at a time, calculate the mean, plot the mean. And it's done that 7,000 times. So 7,000 groups of 30 are summarized here in their means. And sampling distributions, here's the other thing the central limit theorem says, is that the sampling distribution should be relatively symmetric bell shape. And this one's got a little skew for two reasons. The population is skewed and 30 is not actually that big of a sample size. Bigger the sample size, the more symmetric and bell shaped this will be. And the closer this mean of the sampling distribution will be to the mean of the population. Notice the population mean is 4.51. Every sample here has a slightly different mean, and as I move my mouse through, you can see them change down here bottom right. Okay, so population, sample, sampling distribution. Each sample will vary widely in their means, but when I accumulate them all together, the mean of the means is about the same as the mean of the population. Okay, so central limit theorem, two big ideas for us. One, sampling distributions will have this normal distribution shape. Two, the center of the sampling distribution should be about the center of the population. And this works for means, and this works for proportions, the two things we're focusing on right now. So in summary here, we have this population. At the moment, I picked baseball players. 2019 baseball player. So that was my population. My parameter was their mean salary. Salary probably doesn't have two L's. And then that mean is 1L, good, 4.51. So that's what we call mu, 4.51. Now we also have a standard deviation, oops, wrong button, which is the spread of the original population. So that would be 6.334. That's what we call sigma. That's the standard deviation, STD. Sample. We have tons of samples here. How many samples do I have? 7,200. So I'm just going to pick one of them in this region over here. All right, so that one of my samples had n is size 30, had a mean of 4.82. So one of my samples, n equals 30, had a mean x bar of 4.82. It also has a standard deviation. For a sample, we call that S. So STD is called S for a sample. And that particular one had a standard deviation of 7.235. 7.235. We're not going to get into what the central limit theorem says about the relationship in standard deviations precisely, only a little bit next week. All right, next thing I have is the sampling distribution. So that's this one right here. So here I have 7,000 different samples, all of size 30. And the mean of all of these means is 4.504. So red, my sampling distribution. So for a sampling distribution, we call it the mean of the means, like that. And you don't have to worry about that notation this week. We'll go over it again next week. 4.504. It has a standard deviation called the standard error. So that's its STD. This is important because we need this as part of the central limit theorem. That's my next big point. According to StatKey, the standard deviation of these means is 1.130 about. 1.130. So a couple things to note here. The mean of the sampling distribution is close to the mean of the population. So that's something important about the central limit theorem. So central limit theorem, this mean right here, is about the same as that mean right there. Individual samples will vary widely, but we rely on those for an estimate of the population. So at the moment, this 4.82 in reality would be my best estimate. Okay. Next important thing about the central limit theorem. Oops, close these. Is this idea about the standard deviation of the sampling distribution, which is called the standard error. SE for short, standard error. And it's the standard error I need to make certain predictions about either hypothesis tests or confidence intervals. So this right here is important for confidence intervals. I've gone over this in a couple of examples related to that 95% rule in hypothesis tests. And what we talked about last class and some previous classes is when I'm trying to predict, say, the hypothesis test p-value, I have to use the standard error to get there. Because remember, to get a p-value, we look at our distribution here and we find what's going on in the tails. So we'll do a hypothesis test in a minute. And when I'm doing that, I'm definitely using this distribution, which means I'm relying on that standard error right there. So we'll compare the randomization hypothesis test using the standard error hypothesis test. And the same thing in using confidence intervals. So again, big points here. These means are going to be about the same. We rely on the sample mean to get that estimate. And then the other big idea is the standard error is needed to talk about the spread in a confidence interval and the p-value of a hypothesis test. So from the standard error, that's going to allow us to calculate the margin of error in a slightly different way, and it's going to allow us to calculate p-values. We did a little bit of p-value stuff last class. We'll do another one today, and then some confidence intervals. So next is the idea of the normal distribution from the central limit theorem.